In this lesson, we talk about solving linear systems by the method of substitution. There are two algebraic methods to solve a linear system of equations: the method of substitution or the method of elimination. We're going to discuss elimination in a later note or a later lesson. So in this one, we're going to talk about how to solve by substitution. We're going to follow this process. We're going to rearrange one of the equations to isolate one of the variables, and then we're going to substitute that expression for that variable into the other equation. We're then going to solve for the variable remaining in the new equation. We're then going to substitute that value into either of the original equations, or in fact any equation that has both of the variables in it, and that'll allow us to solve for the second variable, and then we're going to write a clear therefore statement. The best way to do this is to show some examples. So our first one is requesting us to solve the following linear system by the method of substitution. We have equation 1 and equation 2. I like to put a 1 and a 2 in circles like this just to help me organize my solution. Well, we see that we have an expression for y in terms of x given to us in equation 1. For that matter, in equation 2 as well. So what we're going to do is we're going to take this expression for y, 4x minus 7, and we're going to substitute it in for y right here. And when we do that, sub the y equals 4x minus 7 from equation 1 into equation 2, we end up with 4x minus 7 equaling 3x minus 5. We then solve for x. We can say 4x minus 3x equals negative 5 plus 7, or in other words, x equals 2. Now that we know that x equals 2, we can sub that value in to any prior equation involving both the variables. So we look at the start, we had equation 1 or equation 2. We just choose equation 1, why not? And we substitute the value of 2 in for x. So we can say that y equals 4 times 2 minus 7, and that's 8 minus 7, which is 1. And so we've just solved that x is equal to 2. We solved that back here. When we got to here, we learned x was equal to 2. And then we know now that y is equal to 1. And so we can say that the solution to the system of equations is 2, 1. When we have the two variables being x and y, we often just state the answer as an ordered pair, putting x first and y second. Okay, our next system of equations is equation 1 being 3x plus y minus 14 equals 0, and our second equation being 2x plus 3y minus 7 equals 0. Well, we're going to isolate either variable from either equation. We see here that we can rearrange 1 fairly easily to isolate the variable y. So isolating y in equation 1 gives us y equaling negative 3x plus 14, which we do. What we've now done is we've rearranged equation 1, so we need to substitute that expression into equation 2. So for equation 2, instead of writing 2x plus 3y minus 7 equals 0, we're going to write 2x plus 3 times negative 3x plus 14 minus 7 equals 0. Notice we just rewrote equation 2, putting in a negative 3x plus 14 in for y, because that's what we said. When we distribute the 3 in, we get 2x minus 9x plus 42 minus 7 equals 0. Simplifying that gives us negative 7x plus 35 equals 0, which means negative 7x equals negative 35. Dividing both sides by negative 7 gives us x equals 5. Now we can substitute this value of x equals 5 into any previous equation involving both x and y. So if we go back a bit, we see that this equation right here, y equals negative 3x plus 14, is tailor-made for us to substitute in a value for x and simply evaluate the y. So we use it. Y equals negative 3x plus 14. We substitute in an x value of 5. We get y equals negative 3 times 5 plus 14. which is negative 15 plus 14, which is negative 1. So that means x is 5 and y is negative 1. And so we can say that the solution to the system of equations is 5, negative 1. Since it's an x and y, we can state them as an ordered pair. Our next system of equations is equation 1 being 5a plus 20b minus 5 equals 0, and equation 2 being 3a minus 8b equals 13. Well, we're going to isolate one of the variables from one of the equations. I see here that I can isolate the a fairly easily, and dividing each of these terms by 5 will not give me fractions, so I'm going to do that. Using equation 1, I see 5a plus 20b minus 5 equals 0, which means 5a equals negative 20b plus 5. Dividing through by 5 each term, I get a equals negative 4b plus 1. Well, I used equation 1 to come up with this expression. I'm now going to substitute it into equation 2. So I'm going to substitute a being negative 4b plus 1 in for the a right here in equation 2. So instead of 3a minus 8b equaling 13, subbing in negative 4b plus 1 and distributing, I get negative 12b plus 3 minus 8b equals 13. Simplifying that a little bit gives me negative 20b equals 10, which means b is negative 1/2. Now, I can substitute this value of b equals negative 1/2 into any previous equation involving both a and b. And I look at this one and I say, well, that's tailor-made for subbing in a value for b to determine the value of a. So I'm going to use it. Since a is negative 4b plus 1, subbing in a value of negative 1/2 tells me that a equals negative 4 times negative 1/2 plus 1, which is 2 plus 1, which is 3. And so the solution of the system is a equals 3 and b equals negative 1/2. Now sometimes you'll see that written as 3 comma negative 1/2. But whenever we're using variables other than x and y, I generally write them out. Okay, our next question is asks us to solve this linear system of equations. It's q equals 3 and 3q minus 5r equals 12. Well, we've already got a value for q, so we just have to substitute it into equation 2. Substituting in a value of 3 for q to this equation gives us 3 times 3 minus 5r equals 12, which means negative 5r equals 3. That means r is negative 3/5. So we've got a value for r and a value for q. And we can simply state the solution. The solution of the system is q equals 3 and r equals negative 3/5. Now we get on to some word problem examples. Well, the first one says Simon purchased 11 calculators and 5 protractors for $23, and Hillary purchased 1 calculator and 10 protractors for $4. We want to know how much 1 calculator and 1 protractor costs. So what we're going to do is we're going to let C be the price of a calculator, and we're going to let P be the price of a protractor. So 11 calculators and 5 protractors is $23. And 1 calculator and 10 protractors is $4. Well, I see that I can rearrange 2 fairly easily to isolate the C, so I do that. Since C plus 10p equals 4, I can say C equals 4 minus 10p. I can then substitute this expression for C into equation 1. And doing that, I'll get 11 times 4 minus 10p plus 5p equals 23. 11c plus 5p equals 23. Substituting it in, 4 minus 10p for c, I get 44 minus 110p plus 5p equals 23. And I can then simplify this expression. I get my p term on the left and any other terms on the right. And I see that negative 105p equals negative 21. Simplifying that, I get p equals 1/5. Now we're dealing with money. It's a cost, so we're going to say that p is equal to 0.20. We're then going to take that value of 0.20 and substitute it into any previous equation involving both p and c. Well, a while ago, since we know the value for p, why don't we use this equation that we came up with a while ago, because it's tailor-made for finding out what C equals given a value for P. Substituting in 0.20 for C gives us that C equals 4 minus 2, which is 2. And we've now established that the price of a calculator is $2 and the price of a protractor is 20 cents. Okay, our next question here tells us that Tessa rowed a boat. She rowed it 600 meters downstream with the current helping her in 20 seconds. She then turned the boat around and rowed 600 meters upstream against the current in 30 seconds. And we want to know how fast she can row on her own and how fast the current is. Well, we're going to let Tessa's speed be T and the speed of the current be C. And you might wonder, well, how did we know to do that? Well, oftentimes you're going to let the variables represent the exact things they're asking for. They're asking us for Tessa's speed and for the speed of the current, right in this last sentence. So we're going to let those be the variables. Now, when Tessa rows with the current, the overall speed is T plus C because her effort and the current's effort are helping each other to move her along quickly. But when Tessa rows against the current, her overall speed is T minus C because she's making efforts, but the current is taking away from that. So her overall speed would be T minus C. Now, we know that when she goes downstream, that distance over speed equals time. The distance downstream is 600, and the speed downstream is T plus C, and this equals 20. Now you might wonder about units. Well, we know we're talking about meters, we know we're talking about meters per second here, and we know we're talking about seconds because it was stated that way in the question. So the units, because they are all consistent with each other, meters, meters per second, and seconds, are going to actually, because they're all consistent with each other, they're going to work out. So we get 600 over T plus C equals 20. Well, what we can do now is multiply both sides by T plus C. Distributing that 20 into the bracket gives us that 600 equals 20T plus 20C. Now when we go upstream, we know that distance over speed equals time, but we know that the speed is T minus C. So we can say that 600 over T minus C is equal to 30 because it took her 30 seconds to get there upstream. Well, 600 is therefore equal to 30 times T minus C. Distributing the 30 into the bracket gives us 600 equals 30T minus 30C. And we see now that we've got two different equations, both involving T and C. Well, we're going to rearrange the first equation to solve for T. Okay? The first equation was 600 equals 20T plus 20C. Rearranging that to isolate T, we get 600 minus 20C equals 20T. Dividing every term by 20 tells us that 30 minus C equals T. We're now going to plug that expression into equation 2. And equation 2 was at the bottom of the previous page, right here. So taking that 30 minus C and subbing it in for the T in equation 2 gives us 600 equals 30 times 30 minus C minus 30C. Distributing that 30 into the bracket gives us 600 equals 900 minus 30C minus 30C, or in other words, 600 minus 900 is negative 60C. Well, we can therefore say that negative 300 is negative 60C. Dividing both sides by negative 60, 5 equals C. Well, we've got a very good expression there for C. And what we're now going to do is substitute that value into any previous equation that involved both T and C. And so we looked earlier on our previous page, we had the expression T equals 30 minus C. Now that we know that C is 5, we can say that T is 30 minus 5, or 25. And what that tells us is that Tessa can row 25 meters per second on her own, and that the current is 5 meters per second.